Coalgebras and Coinductive Predicates. Thank you.
Thank you very much. Yes, so actually it's otherwise the title would have gotten too long, but the Enriched also applies with Coalgebras Predicates. And so this is some work that has been for me kind of motivated from several directions. And you see one is homotopy theory, which I'm interested in using to reason about behavior of systems. And so there are several motivating examples. For example, there's something called higher dimensional automata, where we model true concurrency by having geometrical objects, cubes in particular, where you have several actions, and then the number of parallel actions happening at the same time determines the dimension. And so then you can use art with homotopy theory to actually reason about this computation. There are other things, for example, hybrid systems, there's semantics of epistemic and other agent logics, and then geometric modal logic and various other things that use these kinds of geometrical topological models under the hood. But there's not really a good theory that generalizes, so to speak, invariance under homotopy and these kind of things. So that's what I'm interested actually in studying. And there are actually more things that you can do. For example, for the high-dimensional automata, you can detect deadlocks. In hybrid systems, you can detect so-called xeno behavior, which is behavior that is not physically realizable, by using methods from homology and homology theory. So that's then sort of speak the next step after. But let's start with something basic than that. But also you get other kind of structure that people are interested in. And for me, there is the relation. Is that if you want to do homotopy theory, there are various ways. So one thing you can do is you can take coalgebras, I will tell you in a second what they are, but you can relatively easily build out of a quasi-category, and factor on that, you can build coalgebras, and you get a quasi-category. You can do model theories, model categories, you can build model categories in relatively simple ways, but if you actually want to compute homotopies, it gets quite complicated. So nice, relatively recent developments are to combine enriched category theory, so simplicial enrichment, where you have more structure on your morphisms, together with model categories and so forth, to then reason and compute homotopies. But now, if we're talking about enrichment, there are other things you can think about. We can think about this is the forbidden button. You can think about quantitative behavior. You can think about domain theory and so forth, and all of these start to come into the same framework. That's a bit what I'm aiming for. So this is kind of the question from the very beginning, like why? Here's the why. Let's now get to the things that makes that interesting for me. So first of all, let's start with coalgebras. So coalgebras are an abstraction of behavior that systems show, and the idea is really very simple. You have a category with a functor on it, and this functor tells you what is the type of behavior that you can have. Like you can have actions that can happen, you can make observations on the systems essentially, and then the morphism of coalgebras is basically something on the carrier, which this should be a C. So this is on the carrier of C. You don't want to have a map here, such as this diagram, is the obvious thing, what you also do for algebras, is just turn it around. But now you can actually define this in an arbitrary 2 category by universal property. That's a useful thing that we will be using later. And the idea is kind of like take the idea of a comma object or something like that and restrict it. So what do? Well, suppose you have a 1 cell in a 2 category, and you declare C sub f to be the coalgebras for f. If you have a projection into the category C, that's a forgetful functor if you wish, such that if you and you have this cell alpha, which basically gives you the structure of coalgebras, and then the commutativity and the naturality, if you wish, will give you the homomorphism property. And then this thing is universal in a certain sense, making it a 2 limit. We'll not go much more into this, but we will use this later in a very funny way. Like to talk about. Okay. Now, the next part to coalgebra is, well, okay, nice, you can model all kinds of behavior. And now what do you do with this? Well, you want to reason about it. And traditionally, people have reasoned about behavior like this using modal logics. So So modal logic basically have modal operators that allow you to say something about the behavior of the system. For example, you make a transition in the system, then you have modal operators that correspond to that. One saying, for example, for every possible transition, this and that should happen. Or there is at least one such a this and that cause. Right? These are different modal operators. And then there's an area called the Coalgebras and modal logic, and there are various versions of that. But I think that the ones that is most structural and easiest to use for our purpose here is this one. It's basically, the idea is that you have a category B where you model the behavior. And you have a category D where you model your logic. And basically all the operations that you have in that category, it can be kind of algebras, like Boolean algebras for example, that gives you the underlying connectors for your propositional formulas. And now, what do you do with the modal operators? Well, you require that there's another functor on this category, which has an initial algebra. So this is the alpha here. Alpha is an initial algebra for this functor, and that's kind of the syntax of your modal logic, right? So you take formulas, and you freely generate over that stuff with modal operators. And then you require a dual adjunction between these two categories. And this really gives you a way of interpreting behavior of systems on the other side in algebras. And so people have done this kind of in various ways, trying to make this more and more general, but I would like to also show you somewhat a more conceptual structural thing what sits behind it. And what is very important here is that you have a distributive law. So distributive law basically says, well, given a modal formula, how do I interpret it using the behavior of the system? That's what this thing says. So this can be used to give semantics, and we'll see in a second. Yes.
Is that rule the same as?
Yes. Oh yeah. So there's how would you say that? A trick here. So there's an op which turns everything around. So in fact, you will see that in a second when I have a proper diagram. But actually, so since you're going into the opposite category, you can essentially get a natural transformation in that opposite category, which is the reverse thing in the other one, which is and people typically they use this one, but actually conceptually it's better to think about this one. You'll see in a second why. But now the thing is, so this is nice. We can reason about now the behavior of systems, but it's really restricted to reasoning about behavioral equivalence, bisimilarity, whatnot. Meaning, there's this classical Hennessy-Milner theory, which says if you have a labeled transition system finitely branching, then bisimilarity, meaning the equality of behavioral states, is the same as logical equivalence, which means, well, either you can prove that two things are bisimilar, or you can find a formula that distinguishes it, right? So this gives you really a nice value. That's why people are interested in that. And this kind of picture generalizes it. But now you may not be interested in only behavioral equivalence, bisimilarity, but you may be interested in other kinds of predicates. And so what to do is now you expand this picture. How do you do that? Well, first of all, here on the bottom we have the same story as before. But here we have now a fibration over this base category. This fibration will model essentially the predicate that we want to, or the predicates we want to reason. And so instead of implicitly using kind of what we have here as behavioral equivalence, we explicitly say what the kind of predicate would be that we want to reason about. So this B bar is together with B forms, there are different, how would you say that, philosophies of what people do. Some people assume it to be a map of vibrations, others don't. I do, because it makes things conceptually much easier. So think of this really as an endomap of vibrations, okay? And so now, if you have a coalgebra for this functor up here, over a coalgebra down here, the way you should think of this is that it's essentially a proof for a given predicate, or a given coinductive predicate. Why? Well, so first of all, so we have seen that, so Jacobo was talking about that for algebras, this does not happen. That basically, but here for coalgebras it does happen, namely that if you have a coalgebra for this functor globally, then it actually corresponds to a local thing in the fiber, so you can turn it into something vertical, which is pretty useful here, but that's because it's coalgebras, it's on the other side. And you do that with reindexing. And now what is this here? Well, this kind of says, okay, construct a proof for this specific predicate in this specific coalgebra. And if you take the final coalgebra, terminal object in the category of coalgebras, then this actually constructs the largest predicate for this thing. And that's what is typically called the coinductive predicate. And what is the proof for that? Well, the proof is basically finding any coalgebra for that thing, and then by using the universal property, you get a proof of the predicate. So that's why you can think of this as proofs. So, but for that reason, we were just focusing on that. We will forget about final coalgebras and will not really interested. But now, what you want to know is, okay, suppose I have a system, and I have some kind of predicates over that, and I can turn this now into some logic here. And now, what is the relation between the two? And so, on one hand, you would like to say, well, whenever I have something in my formula, my logic, and I can prove it, well, it should correspond to something in the original defined predicate, and vice versa. I can have all the predicates, and I can find formulas and proofs for them, right? And so the way to do this is that, well, there was this distributive law down here that related these two things. Now I would like to have another one up here that relates the formulas above it. So let me show you this in an unfolded way. And this is where the more conceptual view comes in. So let me step back for a second and introduce you to a category which I find kind of funny, and I think people have thought about something similar already. So I talked about that with Fosco briefly. So what you see here is basically a vibration here, a vibration there, and then you have endofunctors, if you wish, on these vibrations. Endo maps of vibrations on the left, endo maps of vibrations on the right. And then the morphism between such endo maps is essentially here functors going that way, such that the square in the front and in the back, they are maps of vibration, but the top and the bottom, they commute only laxly. So there's a two-cell in between. And what is this two-cell? Well, that's exactly the distributive laws we're interested in. And now you can show that there's a functor from the category of these things into the category of vibrations, where I write the W is saying that, okay, we have functors between them, but not necessarily maps of vibrations. So that's not something you get because of this weak commutative. And moreover, actually, in the original sense, what I said, that that these things form a coalgebra object, so they fulfill this property of this universal property. And that's something we'll use in a second. But for example, if you take all of this map here and you turn it into something on some pair of functors between vibrations, then, for example, if this functor up here, this here, is an equivalence and the functor down there is fully faithful, then actually you get a map of vibrations. And that's not such an uncommon situation. So let me show you that here in our concrete example. So I basically, you remember there was this triangle kind of with all the junctions. This is now unfolded, right, into this cube. So you see here is the identity vibration, maybe on that side. But so you see here is the row bar, that's the kind of lifted thing, that's the thing with the bar I was thinking about upstairs. And the row downstairs here. And so now, with this construction that I just mentioned, this is mapped to a square like this, where basically you get the coalgebras here for B, these are your proofs for B bar predicates, then you have coalgebras that are modeling the actual behavior, and now here on the right hand side we get D with this functor L on it. Now this is called opposite, and so if you take the category of coalgebras on the opposite category, you get the category of algebras, right? That's exactly what you see here on the right. So basically, this view tells you, okay, we can turn a coalgebra into an algebra. What is an algebra? Well, that's basically what we want for logic, right? We have logical connectors that we can interpret. And now, here's the trick, how everything works out. So we have our initial algebra for this functor. And so since it's initial, for any choice of coalgebra here, see, you get a map from alpha, an algebra homomorphism from alpha into whatever thing we have constructed here. And now, since this is an initial algebra, that gives you actually a universal natural transformation from the constant functor into this functor here on the right, and the same here. So both upstairs and downstairs, and they're actually related by taking the natural transformation downstairs, whisking it with this functor, and then you get the one up there. And so this is something that is called adequacy. Why? Well, because if you take the semantics, that's basically what this S is, the semantics of formulas in your system and in your predicates, you get something that agrees with what you have built here and built there. So this is what people call adequacy. Okay? And now what about the other direction? So the other direction is expressiveness. And what does that mean? Basically it means that I want to get a proof for anything that is provable. And I want to get a proof on the side of coalgebras, right? So I need to find a coalgebra, given a coalgebra, given a proof for a formula. I want to find the corresponding proof with the predicate that I'm actually interested in. So I can express everything there. The way this proof goes is you need a bit more assumption. And so it relates to various other words and generalizes that what you need is essentially a weak factorization system in the base. But actually, the funny thing is, it doesn't really matter what kind of weak factorization system you use, but it gives you extra flexibility. And so Bartlett Klin uses one which uses epimonos, an orthogonal epimono factorization system, but it doesn't do vibrations. And then, sorry, why do I write Klin? This is really supposed to be booked here. They use trivial factorization systems where the left class is all morphisms, the right class is isomorphisms. But now you have an extra flexibility, so you can vary your proofs. But anyways, what the main ingredient you need is this one. And what does this thing say? Well, it says if I have a formula here, then I want to turn the thing that I would interpret it in my initial algebra into something that I can do by kind of running a proof on the predicate, right? So and this allows me to turn something in L, which are the model formulas, into something in systems where that's the target predicate. That's the main thing. And so then you can actually construct from a given algebra, you can construct a coalgebra graph which models all the proofs of all the formulas that are valid in that system. Okay. Now, let's, so this is kind of the kind of picture I'm aiming for. And now I would like to step back a moment and talk a bit about more general things you can do with coalgebras, because towards doing this commodity theory for coalgebras, we need more structure. For example, we need the monoidal structure. And this is it's a bit orthogonal to the rest, but I think it's very nice to talk about it because we have heard many things about these things as well. So, for example, if you have a symmetric monoidal category, and you have a symmetric monoidal functor where this means lax, okay? So this lax is implicit, it's not strict or strong. Then actually you get monoidal structure on the category of coalgebras. That's pretty useful, and actually this corresponds to many synchronization products. So if you have two transition systems, you want to synchronize them, that's exactly what this thing does. And now, what happens is that if you have, to do enriched category in this setting, what you do is you get an enrichment on the category of coalgebras, and actually it turns out that this is exactly a coalgebra object in the two category of enriched categories over V. So that there are many examples of this, like for example, simplicial categories, lattice, or and then the monoidal structure, you want to limit that to vibrations. And so this is something I think many people have been thinking about that here. And there are various ways of looking at that. And so one way of looking at it is you have structure in the fiber, and you have structure globally on the whole thing. And then you can ask how they relate. And it turns out that they do relate if you have products at the base. So, for example, if you have a Cartesian monoid product here in the base, then you can construct a global one, and vice versa, you can construct a local one. But how that works if you don't have Cartesianness, I don't know. It seems they differ quite a bit. And you're not even able to do it. For example, the tensor product on vector space, I would not know what to do locally. I only know how to do it locally. And then there are other interesting examples that I want to talk about, I guess. But so you can do families of modules indexed by monod, and you can do deconvolution, and then you can look at what happens locally and globally. That's kind of a fun one. And then for enriched monoidal categories, there's a zoo of things. And I just want to flash this to you. You can look at that later if you wish. But I added my own one here. And the reason for that is that it actually gives you a nice theory, and so that's the last thing I will tell you about this here, is that, and that's where we use this universal property of coalgebra objects. So if you have a category here, V category G, that is so it's enriched over V. You have an endofunctor on it, and then you have a fibration on its underlying category, right? So the fibration doesn't induce directly the enrichment. Then actually you can construct a fibration here in the same way, where the underlying category, the coalgebra category, is enriched over V, and you get a fibration on the underlying category. And the proof is actually quite neat. That's why I wanted to flash that. It uses essentially that the underlying functor is a two-functor that is represented by the tensor unit, and preserves then these two limits, and then exactly we get an isomorphism of two limits, and that allows us to give back composition with one vibration. That's kind of a neat proof of this kind of stuff. Yes, that's true. So there's various other things that I would actually discuss later, maybe with other people, and lots of open questions.
What is your favorite open question?
My favorite open question? Actually, I think the relation between all these notions of enriched vibrations. Because this is like a whole zoo, and I mean there are some things that are kind of clear, but others not so much, really. And then for some things you have Gaussian deconstructions, and for others I don't know, or you may not. And the same actually holds for monoidal vibrations. It's also a zoo of things, and it would be interesting to see that. And in fact, so one of the vibrations that I have been looking at is something that's actually another interesting question. Like, where does this gadget come from? It's basically you have partial equivalence relations valued and quantile with all the kinds of expected things you would have, and functional relations between them. But then there's also various questions that you may have about this one, which is like, what is actually the interaction between the vibrational structure and the enrichment, except that, of course, this is on the underlying category, so you get something in the home object. But, like, for example, in this particular case, does reindexing, for example, preserve the structure? I don't know yet. Maybe it does, and maybe there's something more general to be said also in the context of what we heard about completions. You see, very much like one of these completions, except that in quantiles, the binary operation is not neat, but something else. So then, maybe soon.
Okay, thanks.
I'm sorry we don't have time for another question, and we thank again.